Hi, I'm Ryan,
Hi, my name is Cameron.
Tran.
I am Saki.
and we will be presenting the Jarvis March gift wrapping algorithm.
Okay, so the first thing we're going to be doing is comparing the problem to an analogy so everybody can have a better understanding of the problem. So the analogy we're going to be using to compare the Jarvis March algorithm to is the gift wrapping analogy. So the analogy is basically you have to imagine it's like Christmas Day and Christmas Eve and you're wrapping a piece of paper around a strangely shaped present, and that's basically what the Jarvis Marsh algorithm does. So after that, we have the problem statement, and the problem statement is like a given set of points, including P1, P2, P3, all the way to Pn, that contains endpoints, and we have to give the boundary points of a convex hull that wrap around the entire set of points. And the input would be all the set of points. It's displayed in the image on the left, and the output would be the set of boundary points, which is in the image to the right. So going further into the problem, what is a convex hull? So the Jarvis March algorithm computes the convex hull as a given set of points, and the convex hull is the smallest convex polygon that encapsulates all the points of the set. A convex polygon does not have any concavities, and so that is shown through these images. The first image is a convex hull because it has no concavities. However, the second image is not because you see a point pointing inwards, which would be a concavity.
So, given the set of points here, as we see here, we want to be wrapping the points given in the set here. So, we can start this algorithm at the leftmost point in the set. And why do we start at this point? Because we know that the leftmost point, or any extremum to be honest, will be part of the convex hull. So just for our algorithm, we'll start at the leftmost point here. So we can call this leftmost point here point P. And we want to just pick any point in the set, doesn't really matter. We'll call it this arbitrary point T. And the line from P to T will make a vector going from P and traveling in the direction of T. So we want to be comparing this vector pt to every other vector that can be made with the rest of the points, right? So we want to be comparing this vector pt with another vector pu for some other point u in the set. So in this case, any of these could be u really. And so there are three things that can happen with pt, with pu with respect to pt. One, so if we say this is pt, then the first case that can be made is that pu is clockwise with respect to pt, meaning that if we start at t and we travel in a clockwise direction, we will end up at a more clockwise position at pu. And so since we want pt to be the most clockwise edge in the set of points, we want to be updating pu with pt, as stated right here. Next, if pu is collinear to pt, meaning they are along the same line, we want to first check if pu is shorter than pt. Since if pu is shorter than pt, we need to include all points on the line that are collinear. And so if pu is shorter than pt, we want to be including the edge pu into the convex hull. And finally, if we see a line pu that is counterclockwise to t, meaning that if we start at pt and we travel in the counterclockwise direction and we end up at pu, then we know that this point is not the most clockwise vector to be made in the system, and so we can immediately say that we can ignore this edge pu as it is not more clockwise to pt than pt. And so basically we repeat this process for every other u. So we'll check this point with respect to this point, and this is more clockwise to this, and we'll say this is more clockwise to this point, and we'll say that this point is more clockwise to this point, and finally we'll arrive at this line right here. This is the most clockwise point in the entire set as there are no other points that are more clockwise to this edge PT. So we can add the points P and T to the set. And so finally, after all this, we will let the previous T, which is here, be the new pivot P. And so we will be repeating the same thing. We're going to be starting at P, letting some random point be T, and then we want to be checking if this is the most clockwise or counterclockwise point in the set. And so just quickly going over some pseudocode, we're starting out with P being the leftmost point. We're including P in the set, and while we're not back at the beginning of the boundary, we want to be including points that are clockwise. And so the most important thing here is that we want to check this orientation of P, T, and U. So this is PT and PU. So the question here is, how do we check the orientation of the vector PT with respect to PU?
Given the points A, B, and C, how do we find the orientation of vector AC with respect to AB? We can do this by using the cross product. The resulting outcome of the cross product will tell us the orientation of AC with respect to AB. If the resulting outcome is greater than 0, then AC is counterclockwise to AB. If it is less than 0, then AC is clockwise to AB. If it is equal to 0, then AC is collinear to AB. The running time of the algorithm is determined by n, which is the number of points in the given set, and h, which is the size of the output. Since we look at n points h times, our average runtime is O of n times h. Our worst case being if all the points in the given set lie on the boundary of the convex hull, giving us a total runtime of O of n squared.
Here is an example of using this algorithm to find the convex hull of this given set of points. So first, we determine the leftmost point of the set. In this case, is J. We know that this point must be in our convex hull, so we add it to the output set S and make it our pivot point. Next, in order to find the next point in the hull, we want to find the most clockwise vector that is formed by this pivot point and all other points in the set. And we want the most clockwise vector. So let's choose some arbitrary point in the input set. Let's choose D and name it T. Then we choose another point. Let's choose I in this case, and let's name it U. So we want to check the orientation of PU with respect to this vector, PT. And using the cross product, we have a result of a positive number. So we know that PU is counterclockwise to PT. And we want the most clockwise vector, so we do not want to update PT equals to PU. So let's choose another point in the input set. Let's choose F this time. We want to check the orientation of this vector PU with respect to PT. And this time the cross product returned a negative number, so we know that PU is clockwise to PT. So we want to update our PT vector. So now we have this new PT vector, and we will continue iterate over all the vectors formed by this pivot point P and the rest of the points in the input set. So finally, we have this vector PT. It's the most clockwise vector formed by pivot B. And this vector is JC, so we know that C must be in our convex hull, and we add GC to the output set and make it our new pivot point. So now we have C as the new pivot point. We repeat the process of finding the most clockwise vector and to find all the points in the convex hull. So in this case, H is the next point, so we add H to the output set and then make H our new pivot point, and then repeat the process. Now it's A, D, I, and finally J. But note that this PT vector is pointing from I to J, and J is already in the output set. So we know that we have reached the very first point of our convex hull. So we know that every point has been fully graphed, and we're done. So we stop iterating. And we have this result of a convex hull that grabs every point in the set, and the set of the vertices of this convex hull.
Thank you for listening.